good morning. More energy. And in particular, what we want to do is move on looking at examples of conservation of energy. So, previous class, we had introduced the idea of using something called energy conservation. Let me track that down. Energy conservation to relate potential and kinetic energies for objects that were moving through different elevations in a gravitational field. And we had gone through some arduous formula derivations, but when we came out from all that, what we had developed were some pretty straightforward formulas that we could work in terms of. And so let's look at, I guess this was the last example that we had looked at with the roller coaster. Let's go back and take a look at the setup on the problem. So we had gone through this very quickly. We had a roller coaster at different elevations, and what we were saying is with this new idea of using energy conservation, we could pick different locations along the path of the roller coaster and say if air resistance and friction, if those effects are negligible, then the mechanical energies, the potential and kinetic energies combined, would be equal through the entire process. And so that's what we're looking at here, is we're looking at, here is the roller coaster. It dropped a distance of 40 meters down to point B, and we were able to go through and using energy conservation by taking the kinetic and potential energies at the starting point, kinetic and potential energies at the final point, we came up with a velocity formula using energy conservation. We were able to figure out what the velocities would be. Now, what would happen if, they ask us, if instead of dropping 40 meters, what if we've only dropped halfway? What if we've dropped to here? Well, what we did was we took some ratios, we took that formula and we wrote it down twice. We wrote it down for different heights. Now the way this is working is the formula we came up with assumed that we would be halfway down. So what I ended up doing was redefining the 0 point here and then calling that 20 meters. So if we do that, if we redefine the 0 point to be halfway down and the top point to be 20 meters, then we can use the ratios of those two formulas. And using the ratios, we're going to get some cancellation. We're going to get cancellation of the gravitational fields, and we're going to get cancellation of the factors of 2. And that means that the squares of the velocity are equal to the ratio of the squares is equal to the ratio of the heights. And since the ratio of the heights here were given by a factor of 2, we followed that through the calculations and determined that halfway down it would be traveling at 70% of its final speed. It would be traveling at 19.8 meters per second. So here's another example, pretty similar to this. We're starting at some height. Now remember, we said that by the time each of these persons slides their way down to the bottom, they should be traveling at the same speed, assuming that friction is a small effect, air resistance is a small effect. Then dropping through the same height should end up giving each of them the same speed at the bottom. Now, is it going to take, I guess part A says how do the speeds compare. So the speeds at the bottom are going to be the same. It's part B, I guess, that I'm anticipating here. Part B says who gets there first. Now, they both start off at the same speed at the top. They both end up at the same speed at the bottom. Does that mean it's going to take the same amount of time for each one of them? And it doesn't. What's going to happen here is they're not traveling the same speed between the starting point and the final point. So that's also going to play a role here. It's not enough to say that they started out with the same speed, they ended up with the same speed, therefore it's going to take the same amount of time. What we're looking for is who picked up speed faster, who on average was traveling faster. And I think we have to go with Kathleen here. So this path that Kathleen took dropped immediately. So she's picking up speed right away. And so she's going to be traveling at a higher speed. It actually looks like her path is maybe the same distance, total distance traveled. But in any case, she's going to be traveling much faster early on. Paul, it looks like, is not going to really be starting to pick up speed until here. So Kathleen's going to spend her time going faster than Paul. And so as a result, we're expecting Kathleen's going to reach the bottom first. Now at the bottom, they'll both be traveling at the same speed. Eventually Paul is going to pick up the same amount of speed. It's just going to be over an extended period of time. All right. How do we decide when we're presented with a problem, which approach should we use? Should we go back to Newton's laws of motion, using forces and acceleration, or should we work with energy conservation? And what they're suggesting, and we talked about this a bit last lecture, is that if we have forces that are either constant or forces that are easily manageable mathematically, if we have a simple set of forces that we can easily manage the mathematics, Newton's laws, drawing the force diagrams, calculating the accelerations, works really, really well. If the forces are, first of all, both approaches work in either case, but work in energy, here it's saying, well, work in energy is pretty good too if the forces are constant, but it also could possibly work if the forces aren't constant. So there are going to be situations come up where energy conservation will allow us to set up and solve a problem where forces and acceleration might just be too difficult to come up with. All right, here is that pole vaulter. This pole vaulter was at the beginning of the chapter. It says estimate the kinetic energy and speed required for a 70 kilogram person is going to just barely make it over the bar at 5 meters in height. 5 meters, 15, 16 feet. Assume that the vaulter's center of mass is initially off the ground by 0.90 meters. Uh-oh, this sounds like it's getting complicated. And it reaches the maximum height at the level of the bar itself. So I think maybe we need to take a look at a diagram for that. Let's see what's going on here. So yeah, so here's a stick figure here, and here's a stick figure here. Here's the pole vaulter here. And the idea is the pole vaulter is going to pick up a lot of speed. And the pole is not so much going to be lifting the person. Now, I'm skeptical as to whether this is really the way pole vaulting works. I wonder if it is. But what they're saying is that the person actually is not pushing themselves up using the pole. What the person is using the pole for is to redirect their motion. So, I mean, if the pole is pushing down into the ground, that becomes work. The pole is pushing up on the person. That's adding to their kinetic energy. And so, in order for this example to work, you have to assume that the pole itself is not being used as a way to bring more energy into the system. And I'm guessing it is. I don't know. I have never done any pole vaulting. But here is this person coming through, 70 kilograms, and it says that, now, when we ask about height for gravitational potential energy, where is the gravitational potential energy for this person, or how much is there? And what we have to work from is the center of mass. So, you know, kilogram for kilogram, there's more potential energy in a kilogram near the top of the person than there is near the lower extremities of the person, we can average over that gravitational potential energy by considering the center of mass. So what they're saying is, let's treat all the mass as if it's concentrated right there at the center of that person. And they're saying that they went out and measured that, and it came out to be 90 centimeters off the ground. So the person already, they're not pole vaulting from being flat on the ground. They're pole vaulting with a center of mass that's already a good portion of the way off the ground. Now they're saying that at the top of the barrier that they have to get over, the center of mass, again, we got to think in terms of center of mass here, is at 5 meters. Now, also my understanding with pole vaulting was you curve your body, right? Don't you curve your body in a way so that the center of mass, well, maybe not. I mean, this looks, so the center of mass is here, and then here, and here, here, here. It does look like the center of mass went over the bar. I thought the pole vaulters were supposed to kind of stay curved and then curve themselves over, and that the center of mass never actually goes over the bar, it stays below. But in either case, so a couple of questions that are coming up here. So center of mass to start with, center of mass final, which looks like it's over the bar to me. Is the person using the pole as a way to push themselves up, or are they just using the pole to redirect their motion? So, see, because like here it seems like there's some spring energy in the pole, and that's being used to help propel the person up. So, I'm not sure if this is a good example. Let's see what the example predicts. So we're often left with situations like this. Is the model we're using, is it sensible to be using this model, or let's see what happens here. So we will start with the person running at point A, and then they stick the pole vault down, and somehow they end up over the top. That's point B. Let's use energy conservation. Let's say that the kinetic energy and potential energy we start with can be set equal to the kinetic and potential energy at the top. So the potential energy we start with, UA, is mgHA, and we said the center of mass was at 0.90 meters, and putting all the numbers in, what was the mass? The mass was 70 kilograms, gives us 617 joules. So there's 617 joules of potential energy that we start with. And then once we're at the top, that height, the distance from the ground up to the center of mass, goes all the way up to 5 meters. And so that worked out to be, if I've got these numbers right, 3430 joules. So those are the two potential energies at point A and point B. Now, kinetic energy at B, we're going to say is at rest. So there's really not much kinetic energy when this person gets right to the top. They're barely moving. So they have used that pole to take some of the kinetic energy, maybe get some energy stored in the springiness of the pole, and then use that to come up above, to go higher in gravitational potential energy. Meanwhile, they are slowing down. Okay, so let's see what this gives us. So if that's the case, if KB is 0, then the kinetic energy we need to start with is UB minus UA. It's the difference in the potential energies. I need to be running with enough kinetic energy so that my kinetic energy can be converted into potential energy, and we can make the jump from 617 to 3430. Now the difference then is I need to come up with 2,813 joules of kinetic energy. Let's see what that would give us. Here is the kinetic energy formula. I solved that for velocity, and when I did that, I put all the numbers in, I checked the units, joules, the kilograms cancel, I'm left with meters per second squared. That gets square rooted. It says that I would need to go about 9 meters per second, 8.97 meters per second. It's kinetic energy to start with in order to get that converted into potential energy and go up over the top. That's a pretty good speed. You know, that's getting close to the fastest runners in the world are not significantly higher than that. You know, a good time in the 100 meters is what, like 9 seconds or so? It's like 11 meters per second. So someone running, a sprinter, might be running at 11 meters per second, something like that. And so this is already at 9 meters per second. But anyway, that's kind of an interesting example. And as I mentioned, sometimes you're just left wondering, is this accurately representing the situation? Maybe that's a reasonable approach. Okay, so just practicing our energy conservation techniques. So here's another example. Let's use a spring. So let's try using a spring with this. What we're going to do this time is we're going to use this spring shooter. Here's a dart gun, and we got a spring in here. We're going to push the dart into that. It's going to compress the spring. That's going to store up some energy. And then when we release the spring's going to be released, and the dart is going to shoot out from that. Here is a toy dart gun. The dart has a mass of 100 grams. And it's pressed against the spring. The spring has a stiffness of 250 newtons per meter. Okay, so 250 newtons per meter and a negligible mass, an ignorable mass. It's compressed 6 centimeters and then released. If the dart detaches from the spring, when the spring reaches its natural length, what speed will the dart be traveling at? So here's the setup. Here is picture A, and here is picture B. In this picture, what energies do we have? And in this picture, all I have is potential. I've got the potential energy in the spring. I don't have any kinetic energy. The dart is not moving. So I'll write here that to start with, I have no kinetic energy. This isn't here. I have no kinetic energy. That's going to go to 0. I have only energy in the spring that's been compressed. So that term goes away. And then in picture B, the object is the dart's moving, but the spring no longer has any energy. So I think those two are going to go to 0, and it's going to come down to this. 1/2 kx1 squared is equal to 1/2 mv2 squared. And here it is. So we'll take the energy at mechanical energy in picture A, set it equal to the mechanical energy in picture B. And the dart turned into a projectile of some other sort. VA is equal to 0, XB is equal to 0. So that formula reduced down to 1/2 kx squared is equal to 1/2 mv squared. So that's what we were talking about, where it's now the potential energy stored in the spring, and that's all going to get converted into kinetic energy of the dart, is the idea. That's what we're looking at. Okay, let's solve this. The 1/2s go away. We're solving for V, so V squared is k over m times x squared. And putting everything in, here is the K value for the spring. Its stiffness, 250 newtons per meter. Mass is 0.100 kilograms. The distance that we compressed the spring is x. Now that's not square rooted, so 0.06. It turns out 3 meters per second. So 3 meters per second, you know, so it's going to travel like 3 meters in a second. That seems reasonable when it shoots out from the spring. All right, questions on any of that? All right, let's look at another example here. Let's see if we can bring in an example, and that's what we're doing here. We've got gravitational potential energy, and we've got springs. and we have kinetic energy. This is a chance for us to go in and look at everything combined that we've talked about so far. So we have a ball of mass 2.60 kilograms. So that's what we're starting with, that sphere. Starting from rest, it's going to be released. It's going to drop 55 centimeters and then strike a coiled a spring. So here is the spring. Here is its natural length. Spring is sitting there. It says that... Oh, we have to find out what the K value is. So they're asking us to find out what the K value will be for that spring. And so we're going to have to pay attention to what happens here. Now, if the K value is really large, what we would expect is that the ball drops, but it doesn't compress the spring very much if the spring is really stiff. If the spring has a really low K value, if the spring is floppy, then the ball will hit, it's going to compress the spring a lot. Now, from the picture, I mean, I don't know what these distances are. Oh, maybe we do. It compressed at 15 centimeters. So it dropped, oh yeah, we got all the numbers here, sure. So let's see, if this is the table, or the spring's here somewhere, we're going to drop it from here, and it hits, and it compresses it about 15 centimeters. So that's a fair amount of compression. Now, the mass of this is 2.6 kilograms, which I'm guessing is probably about the mass of our textbook. So if I drop the textbook onto a spring, you know, from 55 centimeters and it compresses 15, what do you think? How stiff is that spring? So let's get some numbers. We'll get the stiffness of the spring. Is that it? Okay, I think that's it. So those are the three pictures. So maybe this is picture A, picture B, picture C. Now what we're going to need to do is go in to A, B, and C and ask which energies are present. So what do you think? That first picture, what kind of energy do we have? And in the first picture, we have potential energy of the projectile, or whatever we're going to call it. We have potential energy. There's no kinetic. It's not moving. And there's no energy stored in the spring yet. Okay. Picture B, all of the potential energy between here and here, that specific height, has gone into kinetic. So the potential energy is gone, and it's been replaced by kinetic energy. Now, it makes contact with the spring, and then the spring is going to exert an upward force, going to slow it down. The full compression is here, and at this point, what energies do we have? Now, let's look at gravitation. We started out with some gravitational potential energy. Is this zero, gravitational potential energy, or is this one? And we get to decide. I mean, they are suggesting that we call this zero. This is positive potential, gravitational potential energy. This is negative. But we actually can define the 0 point wherever we want. Now, what's going to happen in this last picture then is we're going to have to consider gravitational potential energy and spring energy. So spring energy did not show up in A or B, but it shows up in picture C. Let's see what we've got set up here. We may have to switch back and forth to keep track of all this. So now what they seemed to ask about was just the spring constant of the spring. So I think we can skip picture B. I don't think they ever ask anything about picture B. They could ask how fast it's traveling, but they didn't. And so I think we can skip picture B and just take information from picture A and information from picture C and piece those together. So H is 55 centimeters. Now I called it X instead of Y. I sometimes do that. I have better success using X. So this is 15 centimeters. I'm taking all the gravitational potential energy that we started with here and then setting it equal to the potential energies at point C. Now, if I start at point A and call that mgh, then at point C, I have compressed the spring, but I also have to take into account the gravitational potential energy decrease that happened. So I had to account for not just dropping a distance h, but I dropped a distance h plus x to get down to here. So this is minus mgx. I can bring that over to the other side. What that's going to look like is the energy stored in the spring at the end is equal to the combined gravitational potential energies of the 15 centimeters plus the 55 centimeters. So between pictures A and B, this dropped a total of 70 centimeters. So I can write that as 0.70 meters when I'm looking at the gravitational potential energy term. So this is 2.60 kilograms, 9.80 newtons per kilogram. And the potential energy that I solved for gravitationally has worked out to be 17.84 joules. I was just curious about how much energy we're talking about. And we had all the numbers right there. So I went ahead and solved for that. Now, what I've done here, I solved for everything over there. What I've done here is come back to the algebra and solved for k. So a factor of 2 shows up over here. The k, or the x squared rather, goes into the denominator. And then I have an h plus x here. Putting all those numbers in from that lower equation, I ended up with a k value of 72.8 newtons per meter is what it looks like. Okay, so a lot of setup, and they only ask about one item. Okay, so that's perfectly fine. That happens sometimes. Sometimes we have a lot of setup, and what we're asked to solve is relatively, I don't want to say relatively easy, but it's not as involved as what the setup originally suggested. All right, here's an example with a swinging pendulum. Now, a pendulum is a good example of using energy conservation to find out how fast a pendulum would be moving back and forth. How fast is the pendulum going to move at different locations? So here's the swinging pendulum. It says that there's a bob, which is the lower portion here, which we're going to say is M. Now the cord, or the string that it's attached with, is negligible mass. So we're not going to include the mass of that. It does have a length of L, so we'll include that. So we'll say there's a cord, has a length of L to it. There's a mass at the bottom that has a mass of M. L actually needs to go from the connection point here all the way down to center of mass. So the string actually is a little shorter than L, because what we're assuming here with L is keeping track of the distance out to the center of mass. So it says describe the motion in terms of kinetic energy and potential energy, and then find some speed. Find the speed of the pendulum, of the bob, as a function of position, and then also, by the way, come back and calculate how much tension there is at different locations. So that's a lot, right, that they want us to do. Let's see if we can get that. So, let's think of the pendulum swinging back and forth. Where is it going the fastest, and where is it going the slowest? And if you've swung on a swing, then you're familiar that you slow down right here when you turn around and come back. Right momentarily, you're not moving at all. Momentarily, the velocity goes to 0 at that point. And momentarily, the velocity goes to 0 at this point too. So as you swing back and forth, each cycle, there's going to be a point here where the velocity goes to 0. On the other side, there's going to be a point where the velocity goes to 0. So at those locations, we're at the higher elevation. So it sounds like to me what's going on here is when we're at the higher heights, we have more potential energy gravitationally, but we're not moving as fast. So the potential energy is highest here, and then the potential energy is lowest here, and that's where we're going the very fastest. So this pendulum sounds a lot like what we've been talking about. It's gravitationally driven, and by keeping track of the formulas that we've developed for gravitational potential energy and the formulas for kinetic energy, we are going to be able to keep track of V as a function of theta. So there's this theta naught where we start from out here, but there's a variable theta everywhere in between. So I think we got part A figured out here in terms of V is equal to 0 here, and then it picks up speed. That means the kinetic energy is 0, and then it picks up speed until it gets to the bottom, and then it slows down. So kinetic energy increase, 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 maximum, decrease, 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 0. Increase, 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 maximum, decrease, 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 0. So the potential energy is rising and falling, and the kinetic energy will complement that, right? The energy is sloshing back and forth between kinetic and potential. So what should we do then for potential energy? There's a couple of points that we might want to consider. Is it easiest to set y is equal to 0 at the bottom? That's one option. We could also set y equal to 0 here. They are suggesting to use that lowest point. I'm going to try a different point. Now you can go back and redo the problem, but it turns out that when pendulums are swinging, they're actually going back and forth in circular motion. Now it's not uniform circular motion, and it's not completing a circle, but the pendulum bob itself is moving along the arc of a circle because it has a fixed radius. Now if you've got something going in vertical circular motion, more often than not, I'm going to say pretty much always, the easiest point to define potential energy from is the center of the circular motion. Now that might seem a little crazy. Why would you want to come up and define this as 0? It turns out it's the easiest location. Let's take a look and see how this sets up. So here's my picture of the pendulum. Here we are at point A, where maybe we let go and we release it, and then it begins traveling. When it crosses point B, how much potential energy will it have? And so let's get some formulas set up here. The kinetic energy we start with is 0, and I'm going to say the kinetic energy anywhere else is given by 1/2 mv squared. So what we're trying to come up with is V as a function of theta. This is actually the result here. So this says that V squared, we'll come back to this, but see, we're trying to get V as a function of theta. So I'm going to leave that 1/2 mv squared. Now the potential energies, what I claimed was that if I set gravitational potential energy equal to 0 at this elevation, where the center of the circular motion is located, then the gravitational potential energy here at point A is going to be minus mgh, where h is the distance from the center of the circle down to whatever elevation this is. Now, the elevation there is L cosine theta, where L is the length of the string, or the distance from the center of mass of the bob back to where the string is being attached. And so the gravitational potential energy I'm going to write as minus mgh. The minus sign is because we're below what we're calling the 0 point. And then the h is going to become L cosine theta. So h is equal to L times cosine theta. And putting those together, it turns out that the gravitational potential energy expression is minus mgl cosine theta. That will work. It'll work at point A, and it will work at point B. So at point A, the angle we start off at is theta naught, and I can plug that into the formula and say we start off with a negative potential energy, a minus mgl cosine theta naught. So we're already below the 0 point. And then when we get to point B, some other point, we're going to be even lower. And that expression is given by minus mgl cosine of theta. So those are the formulas that we can use for the gravitational potential energy. So if we take all the energies at point A, here's the potential energy, here's the kinetic energy at point A, well that's going to be 0. That drops out. And then the let me okay, we need one more expression here, huh? What we need to do is, since this dropped out, what we can say then is that the potential, the kinetic energy at point B is equal to the potential energy at point A minus the potential energy at, there we go. So this is actually B. So this is side B, this is side A. I got those reversed. So this is side B, and yes, things are moving, so we've got 1/2 mv squared. The m is being canceled out, but the m is being canceled out because there's a factor of m in each of these expressions. So it turns out it doesn't depend on what the mass of the pendulum is. Now, this is the kinetic energy at B, this is the potential energy at B, so I'm adding these two together and setting it equal to the energy that we started with. So the energy we started with was gravitational potential energy. Okay, and I can work with two formulas of gravitational potential energy that have minus signs in them. That's okay, as long as they're consistent. So the m's cancel out, and we're getting v squared is equal to 2 gl times cosine of theta minus cosine theta naught. And that's the, that's the expression that we're looking for. Now, it's not one of those formulas, at least for myself. It's not one I can look at and immediately see what's going on. Let's try a couple things here. What happens when theta is equal to theta naught? Well, when theta is equal to theta naught, this all drops out, and it says the speed is 0. So that checks out. That's how it's supposed to work. Where would the highest speed be? And the highest speed would be right at the bottom. So right at the bottom would be 0 degrees. Now right at the bottom, the cosine of theta term becomes 1. The gravitational potential energy becomes minus mgl right at the bottom. That's going to be the fastest speed. And yeah, that works too, because if this becomes 1, that's the largest value cosine theta can become. So at theta equals 0, this term maximizes. We keep subtracting off this value of cosine theta naught. That's going to give us the largest speed possible. Okay. So anyway, energy conservation allowed us to go in and determine how fast we would be traveling at each location along the swing of a pendulum. Now, you might have noticed, maybe not, is there anything here that tells us how much time it's going to take for the pendulum to swing back and forth? And there isn't. So typically in these energy conservation problems, go back and look at all the examples that we've looked at, timing is not included. So energy conservation does a great job of relating heights and velocities, but it's not immediately clear how you go about calculating timing effects. Now, once you've got the velocity, what you can do is go back and integrate the velocities over time. So there are techniques, but they're moderately difficult to go back and get timing information. So the good news is energy conservation does a great job of relating position and velocity in a problem, but it's fairly challenging to go back and determine timing information. So we're just not going to look at examples where you have to do that. But that is something that you can look forward to in your upper division classes. Okay. Actually, there's one of the labs that we do that involves timing using a pendulum with a gravitational field. So the lab that we do with this, it should sync up with this. So the lab that we're doing, the energy conservation lab, does go back and get timing information. And that's a good example to see what that involves. All right, here is the diagram that I set up. We're going after tension now. They wanted us to calculate how much tension is in the string. Now that's going to vary. The tension in the string is going to be larger at the bottom, maybe? I'm trying to think back when I swing back and forth in a swing and I lift myself out of the seat, I grab the chains and I lift myself up. Where do I feel the heaviest? And I feel the heaviest at the bottom. It's the most difficult to pull myself out of the seat when I'm at the bottom. Let's see why that might be. From the force diagram that we set up, what we've got is a tension directed back towards the center of the circular motion, and then I've got a gravitational force. Well, the coordinate system we want to use as this thing swings back and forth is one in which one of the lines is tangential and one of the lines is radial. So we had looked at examples of that back with circular motion, and so here we are looking at pendulum in energy conservation, and we're using that again. So the tension is here. mg cosine would be this direction. mg sine would be here. Remember those tipped rectangular boxes. Theta is here, and so for the radial direction, there is an acceleration going on. This is circular motion. And so the circular motion, the acceleration is given by v squared over the radius. Now, when the v is 0, right when it momentarily stops, there is no radial acceleration taking place. That drops to 0. And at that point, t will equal mg cosine theta. But anywhere else, we have to take this into account. And so I'm going to set that acceleration equal to, there's a radial acceleration, that's going to be tension minus mg cosine theta. And it says that the tension then, that we're going to end up with, the tension in the string will be equal to mg cosine theta plus any acceleration that's going on. And again, the acceleration will be given by v squared over L. So that's how much tension is in the string. And that is telling us that it's going to be the highest right at the bottom. Let's see. On the previous page, we had derived this formula that the speed squared was given by 2gl, cosine theta minus cosine theta naught. And what we can do is take the v squared that we ended up with here and add that in. So that's what I've done here. I took the 2gl, substituted that in. When I did that, notice that the m over l v squared becomes 2mg. Well, that's handy because the tension term over here has mg also. And that says if we just add everything together, the tension in the string is equal to mg, gravitational force, times this expression of angles. So it's going to be 3 times the cosine of the angle that we're looking at, minus 2 times cosine theta. And I hope I got all that right. Let's see, there's 2 of those here, plus 1 makes 3. There's only 2 of these subtracted off. So that looks like the tension. Now, again, we could ask, okay, where is the tension going to be the greatest? And the tension is going to be the greatest where cosine theta peaks. And cosine theta will have its largest value when theta is equal to 0 degrees. So at theta equals 0 degrees, that's going to become 3 minus 2 cosine theta naught times mg. That's going to determine what the tension will be. And again, it's going to be the largest value there. What does happen when, let's ask this too, I guess, what happens at the edges where it comes in and slows down and stops? When it stops, what's theta equal to? And when it stops, theta is equal to theta naught. So that would be 3 cosine theta naught minus 2 cosine theta naught. That's cosine theta naught. And we can see that if this thing stops at this point, there's no radial acceleration going on, then t is equal to mg cosine theta. So it appears to be making the right predictions. All right, now we kept talking about the radial acceleration. Is there a tangential acceleration going on? And absolutely there is, right? There definitely is a tangential acceleration. The tangential acceleration is given by mg sine theta divided by m. So the tangential acceleration is g sine theta. And we would have to integrate that to find out, as a function of theta, to find out what rate we're picking up speed along the way. So rather than doing that sort of an integration, we have energy conservation. So energy conservation takes care of that for us. We don't have to do the detailed, the variable acceleration of mg sine theta over m. We can just use energy conservation to figure out how fast we are traveling at that point. Okay, so energy conservation is looking to be pretty useful. So let's talk a bit more about how this is all working. We said that there are these non-conservative forces or dissipative forces, things like friction, which it's not really heat, it's not the force. The friction results in heat being generated. Electrical energy, chemical energy. So outside of mechanical energy, what we're looking at are other types of energy that could be involved. And so the electrical energies and the chemical energies and the thermal energies that we're generating, those are all related to kinetic and potential energies of atoms and molecules, and the friction. So all of these non-conservative forces that we're so concerned about, they're still kinetic and potential. It's just kinetic and potential energy at the level of individual atoms and molecules. So when all of the other energies are taken into account, mechanical energies, kinetic and potential, in addition to all these other energies, all of the changing that takes place is zero. So what that says is the total amount of energy in a system remains fixed. It remains a constant. Now there's one more form of energy that we have to throw in here. When we come back in Physics 4C and look at nuclear reactions and look at particle interactions, we find out that the mass, when we look at relativity really, when we come back and look at special relativity, we find that the masses are not fixed. Mass is not a conserved quantity when we start looking at nuclear and particle reactions. Mass isn't really strictly conserved, even in chemical reactions, but in chemical reactions, the mass differences are so small that we can treat chemical reactions as if mass was conserved. So energy conservation becomes a major principle that just works throughout all of physics. And in addition to everything they've listed here, when we get into Physics 4C, we'll have to include mc squared, the mass of particles, as a form of energy in order to see how the reactions are actually going to be carried out. Okay, so mc squared becomes an additional form of energy. Again, we're not looking at that now, but we will be in 4C. So the law of conservation of energy, one of the most important principles in physics, it says that if we look at a system of objects, the total energy remains constant, which means we have to do a lot of bookkeeping. So if you look at the problems that we've looked at so far, it's kind of like, okay, what are all the types? Here's a snapshot. Here's picture A. Here's a snapshot at a later time. Here's a snapshot at an even later time. Can I go through the list of different types of energies, identify all the energies that were present in picture A, all the energies that were present in picture B, all the energies present in picture C, and then I can set them equal to each other. That's what we've been doing, and it's been getting us through these problems, and it seems to work pretty well. So what are the suggestions here for problem solving? Draw diagrams. Diagrams have been useful in every chapter, right? Every chapter we've looked at, we come back and say, hey, draw a diagram. That's going to help you see what's going on. Determine what system you're looking at. So we want to imagine a box surrounding whatever we're looking at, and say these are the objects we're looking at, and this is where the energy is going to be conserved from, is within these objects. 3 says figure out what you're looking for and decide on the initial and final locations of all the objects. So we need to know where the objects start out in terms of their location and where they end up at some later time. And then choose a, let's say, convenient reference frame. Any coordinate system will work, but we may want to pick one that simplifies the problem. And then set up the energy formulas, apply conservation of energy, and solve. All right, here we are back on the roller coaster, and now we're going to introduce some friction. So we had suggested earlier that at some point we would bring in some resistive forces, and I guess it's time. We're going to start looking at resistive forces acting on some of these objects. So here's a roller coaster, 40 meters up above some lowest point, which they're calling y equals 0. So up here, we're at a height of 40 meters. Down here, we're at a height of 0. And then here, apparently, we're going to be at a height of 25 meters. Now, if there were no friction and no air resistance, none of these non-conservative forces, if we start at this elevation, then we would say, we're fine. We're going to be able to go down here, pick up speed. We're not losing any energy. And that means we're going to have plenty of energy to get over this, 25-meter height. But there is friction, and there is air resistance. And so maybe we're not going to make it. You know, if we start from rest here, and we're able to maintain enough of the mechanical energy, we could get over that next peak in the roller coaster, but maybe we don't. So let's see what numbers they've given us. They said that the roller coaster car, when we carry this out, only reaches, oh, it didn't make, oh, I see. I got to stand back farther. I'm missing the height there. So this was probably, what, 30 meters high? It's more than 25. We didn't make it. So the car stopped at the 25-meter mark. Now, one of the things we should point out with all of these energy conservation problems is what happens then is we pick up speed, we're going faster, 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 we go really fast here, and then we lose speed and we come back to here and we stop. Is that the end of what happens? And you go, no, you didn't make it all the way to the top, so this object turns around and goes back, and then it goes back and forth, and if there's friction, it will get a little lower each time, and eventually it will be down at the bottom. All right, if energy is perfectly conserved, then it's going to be able to go up to 40 meters here, you know, but if not, then we could have this back and forth kind of stuff going on. Well, let's see. The roller coaster car shown reaches the height of 25 meters on the second hill. It had traveled a total distance of 400 meters. So that's 400 meters is a long way. Okay, let's see. 400 meters? I don't see the 400 meters here. Let's see. This dropped 40 meters, right? That's the vertical drop. So the distance from here to here is what? Maybe 80 meters? And then back up this side, I don't see where the 400 meters is. But anyway, we're going to go along with that. So we're going to imagine that the roller coaster traveled a total distance of 400 meters going from position 1 over here to location 2. The car's mass is 1,000 kilograms. And what they want us to calculate is determine the thermal energy. How much thermal energy has been produced with this roller coaster dropping between points 1 and 2, how much thermal energy was produced. Now, the amount of thermal energy produced, that's like asking how much work was done by all of the frictional forces, right? So all of the frictional forces combined, what effect did they have? So we're really looking for missing energy. So here we go. Point A, I organize this a little differently here. So at point A, no kinetic energy. We drop to point B, we pick up to point C. At point C, there's no kinetic energy. The heights were different. So the height at point A was 40 meters. The height at point, now I'm calling it C, is 25 meters. And I think I calculated that. Okay, so there's no kinetic energy before or after those drop out. So the energy that we started with was totally potential. The energy when we got to this point and slowed down and stopped is totally potential. So potential energy at A plus potential energy at C plus some thermal energy. So not all the energy remained thermal. Some of it got diverted into thermal energy, and that's, I'm going to say that T is thermal energy, big T, and that's what I'm going to solve for. So the potential energy at A, that's 1,000 kilograms of roller coaster, gravitational field of the Earth, 40 meters. We started off with 392,000 joules. So 392 kilojoules. At point C, we're only at a height of 25 meters. That's only 245,000 joules. So 245 kilojoules there. And then the energy lost along the way, it's got to be thermal energy, right? Things like friction, air resistance, is going to result in the atoms and molecules moving faster. There's more vibrational energy in the atoms and molecules that make up the roller coaster. Some of that thermal energy is left along the track, right? So the track probably heats up as the wheels come along the track. That's going to heat up. That total amount of thermal energy is just the energy that's missing, and we are missing 147,000 kilojoules, I think, is what that works out to be. So, you know, you put up the missing posters, energy missing, we're missing 147,000 joules, and that's what's happened to it. So we can certainly calculate how much energy was lost along the way. Now, if you're an engineer and you're designing a roller coaster, and when you try it out, it doesn't get over this peak right here. Maybe that's not a good thing for your employment if you've designed it and it didn't work. So maybe you underestimated how much thermal energy losses there would be. Maybe there's a way to go back and redesign something, the track or the roller coaster car, so that there will not be such a large loss taking place. Okay, let's see where we are here. I think I'm going to look at one more example. I think we have time for that, and then we will wrap up for the day. So let's do that. Let's take a look at this example here. What we've got is we have a spring, so certainly there's going to be energy stored when we compress this spring. Here comes a block with some speed. That looks like kinetic energy. I don't see any gravitational energy here, do you guys? So I don't see any elevation changes. So it seems to me like it's going to be spring energy and kinetic energy. Oh, you know what I just saw? Frictional forces. So if there's frictional forces, then same as last problem, there's going to be energy converted to heat. And so it looks like we have to keep track of kinetic energies, potential energy in the spring, and we have to keep track of the work being done by friction. How much energy is friction taking out of our system? So here we go. A spring with friction, not in the spring, but friction along the surface. So picture A, this block is zipping along at some initial speed. It hits the spring with force constant K, and that's picture A. Now in picture B, the block has slowed down and stopped due to the presence of the spring. And so in picture B, we're going to have potential energy in the spring, and we are going to have potential energy in the spring. I guess that's it. So we're going to do it first of all without friction. No, I guess we're going to do it with friction. So here's the energy we start with. In picture A, the only thing we have is kinetic energy. In picture B, the kinetic energy is gone. We have energy of the spring. But what we have to take into account now is, along the way, since there was friction, we're going to be generating thermal energy. Now the thermal energy we generate is going to be the work done by friction. So how much energy transfer takes place due to the frictional forces? So again, I'm interested in an absolute amount. So I want the absolute value of that. That's going to be the frictional force acting over a distance x. Okay, so was there friction here? I'm going to go back and reread the problem. I think I know the answer here. So it's traveling at a speed v0 when it strikes the spring. So picture A specifically is right as the mass begins to make contact. So the v0 that they're giving us is at that location. See, I didn't draw the picture quite the same. So the mass is here, and so we're not going to start counting the friction until that time. And so only the distance x applies when we're looking at the energy loss due to friction. Now the frictional force can be, this is kinetic friction. There's a mu sub k times n, and in this picture, I didn't draw it, but there's going to be a normal force here, there's going to be an mg here, n will equal mg. And so I can substitute, the n gets replaced with mg. That says that the energy loss due to the friction, so this is fairly simple. The frictional force we can calculate, or we can come up with a formula, and then we can just multiply that by the distance. So in this case, that algebraic expression is telling us how much energy was converted to thermal. So, of the energy that we started with, which was all kinetic, some of that energy is now stored in the spring, and some of that energy turned into thermal energy, due to the friction. So that's starting energy equals final energies. Now what the heck was it that they wanted us to calculate here? And it looks like what I've done is, well, I was pretty happy with this, so I went ahead and wrote that in. I just noticed my diagram is here. Okay, so my force diagram is here. So here's N, here's mg. Now what's happening here is, when this comes in and slows down, there's a force from the spring, kx, opposing its velocity. That's going to slow it down, as well as friction. Friction is also going to be slowing it down. So I'm glad I got the force diagram in there. I just don't feel like the problem's complete without that. Anyway, I went in and solved for what the coefficient of kinetic friction is in terms of everything given. I hope that's what they wanted us to calculate. It is. Okay, so I did read the problem pretty well this time. If the spring has stiffness constant K, determine the coefficient of kinetic friction. And so I came up with formula. So we developed a formula for kinetic friction. All right. And that's looking like a good place to stop. So if you guys have any questions, stop by office hours and let's take a look at that. We're moving on in the next lecture. We're going to finish up chapter 8, which means kind of we're finishing up all of these energy chapters. Energy is going to be around with us forever. So we're going to keep referring back to energy conservation. But the last topics that we have to look at here involve gravitational potential energy, long range. So we got to go back and rethink gravity in large scale rather than just near the surface of the Earth and how we have to accommodate that. Okay, so have a good day.